That's exactly what we're going to do here. We're going to break this up into pieces. We're going to try and come up with an expression for what the force is from one piece. And then we're going to try and create an expression that tells us how to add up every single piece's contribution. It's the same thing. In order to do this problem, we start in a similar place. Identify and outline all the things that are given, things that we can be in our final expression. So I started this problem by saying that we have a bar which has a total charge of Q. It's spread uniformly along the bar. And I said that the bar is L long. Next, trying to identify where the center of the bar is. Let's say the center of the bar is right there. That okay? That look like center to you guys? Good enough? We have a particle located a distance A away from the center of the bar. So, for the time being, I am expecting an answer that will allow Q, L, and A to be in the answer. These seem like clear given quantities. Now, those may not be sufficient for us to produce a solution, but they represent the result of our problem. What our problem ends with can be those things. Fundamental constants probably will be allowed too. Now, we want to treat this problem the same way we treated the dot problem. But to do that, we need to identify a charge that we can use in this calculation. We know we're looking at Coulomb's law. So generically, it's going to be two charges, the constant, and the separation distance. So let's give this point a charge, not 8, but lowercase q. And to do this problem, we have to identify what we are going to use for q, the big Q. We can't use the whole bar at once because different pieces of the bar count differently. So in order to do that, we're going to identify a piece of the bar. This piece of the bar will be a small piece of charge. So in order for us to have some consistency, we need to find a way of expressing the piece of charge. Now, there's a lot of ways I could go about explaining how we express a piece of charge. One way is just to consider density. If you guys think back to density, chemistry density, we could write the density of this bar in terms of its length. So when I first started talking about this, I talked about different kinds of density. Right now I'm talking about linear density. This bar has a uniform linear density. Any length of bar that I break off, it will have the same density as the whole bar. So the whole bar's density is Q over L, coulombs per meter. Now, can we agree that if I were to break off a small length of bar, say delta X amount of bar, then the bar would have charge that would be equivalent to this ratio. Let that sink in for a minute, but let's make sure we're okay with that. That if I could just slice this piece out, its charge per length would have to be the whole bar's charge per length. Does that make sense? Are we sure? This is a critical moment. I can't move on until everybody has this moment. There shouldn't be a huge difference. Go ahead.
Like I don't
Another way I could word it? No. Is there another way one of you can word it? Because I've given you my words. Well, we know it's been about 15 minutes and he hasn't said a word, so he has to talk. Go ahead, Kyle. And that's fine for a novice to get started. But part of the problem with using delta is something microscopic. If I zoom in here and I think about it for just a little bit, this portion of the bar, you guys see where I'm identifying that portion of the bar? That's closer to Q than this portion of the bar, isn't it? If I use delta, I'm really kind of averaging the answer, because I know the two sides of this piece don't interact with the charge the same. One interacts more tightly than the other because one is closer than the other, meaning this edge of the bar is influencing the charge more than this edge of the bar. I really don't want that. I want this to be as, I want this piece to be as distinct as possible. So there's a mathematical way of saying that when we are slicing off a piece of the bar, we're trying to slice off the absolute thinnest amount of bar possible. So I'm dealing with the absolute smallest amount of charge I can at a time. This is a calculus idea. But what we're really trying to say is this delta x is really small, so that this side of the bar and this side of the bar are close enough together that they don't really have any difference in their in their influence on the charge. Now, again, that's a calculus idea, one that some of you know and some of you don't. But all it really means for us in the short end is to say we're not going to use the word delta. We are going to use a lowercase d instead. dq, and in this case, dx. So I'm going to say that this piece of charge, dq, is a width known as dx. Now, many of you are in calculus now. Some of you have finished calculus now. Calculus likes to use the same variables over and over and over again. They really do. Our variable choice isn't arbitrary. I'm choosing dx because x generally represents length. I'm using dq because q generally represents charge. The representation of the variables we choose here is specific. We are looking at a bar that takes up space. Dx talks about space, where it is, how big it is, how much length it is. So I didn't choose dx accidentally or arbitrarily. I picked it specifically because it represents length in the x direction. It's quite possible in the future I'll have a dy, and I will have picked it specifically because it represents length in the y direction. We choose these because we're trying to find a way to use letters that represent real things in these problems. So that's why I chose dx, but it's more than just that. This piece of charge, dq, acts just like a charge. Therefore, I can begin to flesh out a force expression, replacing the big Q with just a piece, dq. Because we can't talk about what the whole bar does at once. We can only talk about what a piece of the bar does at once. But I'm treating that piece as if it's a point charge. Now, this part's important. This will not be the entire force. This is just going to be one part of the force. So in order for this expression to be more correct, I should definitely say to the world who's watching, this isn't the whole force. This is one part of the total force on the bar. So this expression we're using, this terminology, this symbology of df, dq, dx means a piece or a small amount of the whole. So dq is a small amount of the entire charge q. dx is a small piece of the entire length of the bar, L. I just happen to know that this ratio exists. Meaning I know that the charge density of the bar is the same everywhere. Now, I don't want to have an aside, but I want you to understand that there's a little bit of power here that I'm leaving out. For example, what if the bar has some of the charge more concentrated on the right side than the left side? And what we're doing could help us figure that out too. But we're going to stick with a nice, uniformly charged bar. Now, what we've done is the first part of setting up a force expression. And I like to kind of name these things, so let me provide a name for this. To me, this is the part where you're setting up and identifying your piece of charge. You're establishing what you will call dq. It's essential that we understand that the first part is just identifying what is a piece of the whole. And do we know anything about its charge? In this case, we do. We know that the amount of charge there is equivalent to the ratio of the total charge to total length, the charge density, times how much of the charge we're looking at, how wide the piece is. We are specifically solving for dq. This also allows them to give us something like lambda, a symbol that represents the total charge over the total length. For an infinite bar, there would be no length, so they would just give us charge density. We need to be prepared for that possibility. So in order for you to be prepared and to have something useful in your notes, just be aware that generally the amount of charge is equal to whatever the density is times the size of your piece. If our object was like two-dimensional, our piece could be a small piece of area. If our object was three-dimensional, our piece could be a small piece of volume. So this is a generic way of saying that. All right, I want to go on to the next phase of this. The next phase requires you to invent a way of identifying the location of this piece. We know that ultimately, where this piece is incredibly important. It determines the size of the force. In fact, you should all be very clear or very understanding that there's got to be a way to draw from the point of that charge to where the influencing location is. In fact, we've been calling this R the whole time. R can't be in our answer, but we will need to have a way of identifying the size of R. This means we will probably have to invent some variables that will be used temporarily to help us locate our particle. Things like, well, I'll call this distance x. Why? Because it's horizontal. And I said that my piece was a little bit of x. So it makes sense that I would point to it with a number that's similar to x. I'm telling you that the piece is a distance x away from the center. And how big is that piece? Well, a little bit more. I need that because I need to find a way of writing R in terms of other things. And this is one way to do so. Also, that piece is going to have an influencing force. And that influencing force is going to be like in this direction. It is very likely that this angle is probably going to become useful. So this next phase, I like to tell students to write in their notes is you need to have a way to point to every single piece of charge. You need a set of variables that will tell you where is every single piece of charge. I've decided to use the variables A, theta, and x to tell me where every single piece of charge is. A is going to be the same all the time. The bar is located a perpendicular distance A away. But then my first piece of charge is over here, L over 2 to the left. And I want to include every piece of charge until I get all the way over here, L over 2 to the right. So I'm going to use the variable x to be a placeholder for where every one of those charges could be. I know that I could use that set of instructions. Go straight up A, and then turn left and go a distance x. Or turn right and go a distance x, and you will find the charge. Those instructions are there so that you have a means of pointing at the particle. So that's how I would point at that single piece of charge. Go up A over x, that's where it is. And we've done this before. We've done this because we know we need to replace r with other things. We need to tell our problem how far away is the piece of charge. So the very first thing I would start doing is saying, okay, my df can now be rewritten Yes, I know that x can't be in the answer either, but at least x is one-dimensional. And I know where the beginning of x is and the end of x is. Negative L over 2, positive L over 2. Now, we're not quite done with the identifying where our piece is, but you still need to have a way of identifying its location regardless of what the shape of the object is. You need to find some variables that you can use. And it's not arbitrary. We're trying to find variables that are related to the size of the piece. So I didn't choose to use x arbitrarily. I chose to use x because x is related to how thick that piece of charge is going to be. So I'm using x purposefully because what I'm really telling my problem is that my piece of charge is located a distance x from the center, and it is a little bit more than x, or a little more in the x direction wide. That's what it's really saying. That's what dx is really saying here. Because if I do that, it lets me write my charge in terms of the length of the piece. Meaning one of the two things I'm trying to substitute in here is to remove dq and write the size of the charge in terms of the geometry of the object. So I'm doing two things at once here in this step. I'm identifying where the particle is, where the piece of charge is. And then I'm writing how much charge there is in terms of where the piece is, in terms of the symbols I'm using for where the piece is. I'm trying to identify things that are related to geometry. And it also does a wonderful job of working in something that is constant and will stay the same for every piece of charge on the bar. Sorry to bore you. I'm doing my best. I'm trying to go slow and deliberate. Now, is there symmetry in the problem? This part is not hard, but if there is symmetry, you should probably find a way of utilizing the symmetry to make your answer more complete. I think most all of you know that the particle is going to experience a force along that red line. That as we've been talking this whole time, we know that there's going to be a component of the force in this direction and a component of the force in this direction. And the off-axis components are likely to cancel out. Meaning the horizontal component that points this way will be canceled out by a similar horizontal component on the other side. Everybody follow along with that? We've had this conversation a lot, but what that requires is for us to write cosine theta here. We are only interested in the parts of the force that are vertical and not the parts of the force that are horizontal. Now, I know the bell is rung, but I just want to go one minor step forwards. I want to either decide to write everything in terms of theta or everything in terms of x. And we've been doing this for a while, so I think all of you know we can replace cosine theta with something else, and you should before you walk out the door. There's a whole lot there, but nothing new. And you should pack up, but I will write one more thing as you're packing up. All right, all I've done is reorganize it. I put all the variables together that are constants and pulled them out front. I've left everything that's about geometry here with the dx. I'm gonna start by, and we'll pick this up tomorrow. Just getting rid of this portion. And just kind of hit some high points. We first identified the shape and size of our object. We found a way to describe one piece of the object. We broke the object up into small pieces and therefore found a way to describe how much charge each piece had in terms of its size. We found some variables that we could use to point to where that object or where that piece was. And we started to identify how we could express the amount of force from just that piece. From there, we started to replace variables that we know can't be in our answer with ones that can. Although R can't be in our answer, neither can X, but A could, and this gave us a one-dimensional way of expressing the force. The problem is that this force is at an angle, and we know that there's a certain amount of symmetry. So we first substituted in what we know about the amount of force, and then we scaled it for the amount of that force that was directed away from the bar and ignored the the horizontal components of the force, because we know that for every one that was pointing to the left, there was an equal portion that was pointed to the right. And then recognizing that we were in terms of theta, we made a decision to place it all in terms of x. Now, you didn't make that decision, I made that decision, and I wasn't clear about it. Theta and x are related. Would you guys agree? Yes. So it is plausible we could have done the entire thing in terms of theta if we wanted, but we would have to find an expression for x in terms of theta, which may or may not be easy to do. And that left us with this expression. Now, this next part you may not understand, and it will likely have to do with your limited experience with calculus. But so far, nothing we've done here is calculus. It's all been algebra. Although there are some calculus remnants in here, the dx mostly, and the df. Those are calculus remnants. You don't really know what they mean, but I believe that you could probably replace them with the words a small part of, and you'd be just fine. Meaning, this dx is a small piece of the bar, and I'm measuring it in terms of meters or some length. This df is a small part of the overall force. Now, we want eventually to add up all the parts. That's what I want to do here. I want to add up all of these pieces of the force, all these parts of the total force, so I can get the total force acting on my charge. Now, to do that, and this is worth kind of moving all that out of the way and just rewriting the part that's here. So many pieces. Now, to do this next part, it's just algebra. And you may or may not have the algebra skills to do this. But what I'd like you to do next is go through and ask yourself, which of these things changes when x changes? We didn't use dx here arbitrarily. We used x here on purpose because it is defined based on where this piece is on the bar. We said basically go out a little ways along the bar, and our piece is a little piece in that direction. That's why we use dx. But dx also signifies that x is an important variable. Anything that's a constant, we can ignore for the most part. But anything related to x, we have to deal with as part of this sum. And that's same thing here. I want to recognize that q times k over L, these things will be a part of every single piece of force. In fact, I could probably take out the A too. It will be with every single piece of force. It doesn't change. But I also have this other term, 1 over a squared plus x squared to the 3/2. Every time x changes, every time I go from a different place on the bar, everything here changes. Questions? I can, but I'm going to wait till I have everybody together. You guys good? So, if x goes from 1 meter to 2 meters, there's nothing in here that will change. Right? The bar is 20 meters long, then as long as I'm on the bar, these values are the same all the time. I'm always the same distance away from the bar. The bar is always the same length. It always has the same charge, and my point charge always has the same charge. These things aren't changing. However, if I go from the 1 meter mark to the 2 meter mark, this whole denominator changes. There's no way I can factor anything out of that. The whole denominator is going to change. So I'm separating out the two parts. What I haven't written down is the dx, which I am going to intentionally write all the way to the right. That's a calculus thing. And worth, further exploration later. This all equals df. Now, we still have not done any calculus. What we have done is we've made a statement. We've said every piece of the force is equal to all of these, all of this stuff. If I would like to know the total force, I'll have to add up every single piece. Now, the difference here is that our bar is not a bunch of discrete particles. Our bar is continuous. We want to add up every small piece of the bar, and we're saying that each piece is very, very small. So there is a version of a summation that is not based on discrete pieces. The version of a summation that's not based on discrete pieces, but is based on something that is continuous, is still something that means sum. It's a script S. And for those of you who are new to calculus, it's the integral symbol. But integrating is summing. It's a summation. So we are going to sum both sides. Now, you don't need to appreciate fully what it is we do here. What you do need to appreciate is that this summation will solve the question. It will determine the answer, whether you can do the summation or not. Look, there are summations you will be unable to do. Although I have some happy little calculus folks in here who have finished a semester of calculus, I encourage you to find the answer to this question. It's not an easy one. It is quite challenging. Some of you are up to the task. Go ahead and do it. But it will require an interesting trig identity for you to complete. So if you're into that, knock yourself out. I will say, though, the left side's easy. We're saying add up all of the pieces of the bar. That means I will be getting the entire force on the left. Now the right side has to comply with that, meaning I have to set limits. Those two places where I put circles, they're not zeros. They're locations where I place limits. I tell my problem where the first piece of the bar is and where the last piece of the bar is. So I want to continue that here. But in order to make this, clearer, easier to read, I can take anything that's a constant and pull it outside of the summation. That way I can focus the summation portion on just the parts that change when my variable changes. So I'm going to pull out Q, Q, K, A, all over L, and put my summation just on the part that matters. Yep.
Why are you putting them out of those?
Because I can. Because I can. They're distracting. They're in the way, and they aren't a part of the calculus. Now, people who have had calculus understand that this is an activity. Right? What you learned in calculus is sitting right there. You're supposed to execute that. You're supposed to find an antiderivative and either apply a constant to the end of it, or if given boundaries, you're supposed to apply your boundary conditions. Right now, all the work was getting to this point. If you want to get more credit, you need to demonstrate that you know where the first piece of the bar is and where the last piece of the bar is, so you can tell this problem to add up every piece of the bar. That's not too hard. When you look at the geometry, I'm going to say that the first piece of the bar is located L over 2 to the left side, and the last piece of the bar is located at L over 2 to the right side. Right, not a surprise. If the whole bar is length L, I can start over here, negative L over 2, and I can end over here, L over 2. That's one thing. You could double it and start from the middle of the bar and go to the right, which I think is what Jeremy was going to ask. And that would have been just fine too. I'm not trying to add too many things to this right now. Right now, what I'd prefer you guys do is recognize that you have to add up every piece of the bar. You have to include all of it. If I told you it was an infinite bar, I would put down from negative infinity to positive infinity. As this is only a finite bar, I'm putting from negative L over 2 to positive L over 2. Now, Jeremy's question, which I didn't mean to talk over him or talk for him, was that what you were going to ask? Jeremy's idea of taking the bar and only dealing with half of it has legitimate and reasonable sense, because sometimes If you try to do the whole thing, your integrals don't work out great. And it's hard for you to know when to break it into half and just do half of it, and when to use the whole thing. Luckily for us, we only integrate 3 shapes. So we'll learn pretty quickly which shapes you integrate the whole thing, and which ones do you break in half. This one, I would definitely break in half. But that's not really a topic for today. If you make it to here, which let me tell you, that's a big if, isn't it?
Yeah.
You've done all the heavy lifting. Which is why I always laugh when people say, well, I would never handle this class if you didn't have calculus. Well, yeah, except calculus just tells you the answer to this part. Calculus will never teach you how to create this, which is why calculus is of limited use when it comes to getting to this moment. The AP exam is going to give you about 4 points for constructing all of this and 1 point for doing the calculus. So I don't think the calculus is really the relevant part. Constructing this, that's the relevant part. And one of the things they're going to want to know is that you know where the bar begins and where the bar ends. That's a point on its own. So setting up the integral, that's the big chore. Executing the integral, not so much. Now, I'm not teaching calculus today, so we're not going to execute this integral. You guys who have had calculus, good luck. I will say, you don't have to actually do the calculus, even on the exam. This integral, if is required for the exam, will be located on an integral table given to you on the equation sheet. They will tell you the antiderivative. So all you have to know is how to use it. Again, actually getting that antiderivative, this one's tough. You guys, who's had calculus already? Prove it. You guys know this one's tough. If you don't know it now, try it tonight. It will be. It wouldn't be so tough if there was an x in the numerator, but there isn't. Because there's no x in the numerator, you can't integrate this by parts, and you can't use a chain rule. You'll have to use a trig substitution. I promise. Yeah?
Is this beyond use of, normal use of?
Yep. Yeah, use of won't work here. Integration by parts won't work. To speak to Jeremy's question, though, just for a minute, which is worth speaking to, you can break the bar and just do one side. But if you're going to do that, you have to realize that you have to double it for both sides. One reason that's kind of nice is it introduces a 0. And as you guys have probably grown accustomed to, sometimes zeros make your problems easier if you can introduce a 0. So, do that. So, I want to get us to this point, meaning I want us to be able to work on a problem and together make it to this. Whether we can do anything with it or not, I want to get here. So I have an example that I'd like us to work together. It is easier than this one, but I think it is a good illustration of how to apply these principles together. So that's a good question, and I didn't address it, so let me just come back to this. For those of you who have calculus, you understand this, but those of you who don't have calculus, this is going to be new. We're going to be coming up for a new expression for this, something called the antiderivative. And it will likely have x in it. Now, the reason this is important is every place that we have x in our answer, we're going to substitute either a 0 or L over 2. So our final answer won't have x in it. Our answer will have L over 2 in it, and L over 2 is allowed to be in our answer. The illustration, we're going to take the same bar, so the bar has length L and total charge Q. And we're going to consider a point charge located a distance A away from the bar. So what I've done is I've turned your problem into a one-dimensional problem. Anybody who's had calculus should be able to execute this problem all the way to the end. If you have not had calculus, you may not be able to. That's okay. I'm not looking for you to be able to do that. I am looking for you to consider what it would take to set this problem up. In order to do that, you really need to be the person who does this. But you've never done it before. So what I'm going to do is I'm going to give you a step. And with each step, I'm hoping you can kind of complete what needs to be done. And then I will fill in what the steps should look like, have you done it correctly. Does that make sense?
Yes, sir.
So let's start at the beginning. Can we agree that there is a certain amount of symmetry here? Can we agree that the force on charge Q will be to the right? We all agree? Can we also agree that each piece of the bar will push on charge Q to the right? So this is a one-dimensional problem. That's good. So, step one, draw a box somewhere on your object to represent a piece of the object. Identify with a differential how much charge that piece will have. Since that one might be a difficult chore, I'll do it for you right off the bat. Just DQ. Now, try and define how much charge that piece has based on the size of the piece. Again, try and figure out how much charge that piece has based on the size of the piece. Now, I don't want to write anything, but I gave you a framework for this. I said the amount of charge would equal the object's density times the object's size. I'm going to define this object as having a size dx, a small amount of length. And I'm going to define the object's density as being the total charge, Q, divided by the total length, L. So then I bring all that together, I can say that the charge of this piece equals the charge density times the size of the piece. I'm exploiting linear symmetry here. I'm saying this object is very long compared to its other dimensions, and therefore I'm going to treat it like a one-dimensional object. You'll know if it's not, it'll be two-dimensional. I have an area. Now, the reason I don't treat this like a two-dimensional object isn't because I know automatically. The reason I know that I don't have to treat it like a two-dimensional object is because when I zoom in, does this piece of the bar and this piece of the bar really make much of a difference? Now, this bar is very long compared to how thick it is. I don't think I have to worry about changes in the y direction affecting my answer very much. if my bar was more like a plate, like this, well then if I chose a piece of the bar, my piece probably would have to take into account how high it is or how low it is and where it is. I'd have to treat it like an area then and not a long bar. So this is what I mean when I say look for that kind of symmetry. I think I can reduce this problem to be one-dimensional based on that alone. And it's not a secret. I mean, the problem will tell you, generally. Either because it'll give you something like this and say it has a charge density of lambda, which means charge per unit length. Or it'll tell you that it has a charge per unit area. They'll be pretty clear. This isn't the tricky part. They'll tell you these parts. Tricky part still is coming. All right, so now I usually say the next thing that I think is good to do is try and define where this piece is relative to where your charge is, or your point of interest. This is my point of interest. So to define where it is, I need a variable that tells me where it is. Now, don't choose an arbitrary variable here. We said the piece was dx thick or dx wide. We did that purposefully so that we could point to it using a variable that was reflective of the width of the piece. So I'm going to say this piece is located a distance x away, one dimension. It's located on a number line. Any question about why I chose x? Yeah.
I understood that we chose x, but why aren't we using like a plus x and giving x like just the length of the bar that comes to the x?
I could. There's nothing wrong with doing that. But remember, in a few minutes, I have to tell it where the bar starts and where the bar ends. If I choose x plus a, then I'd be choosing x to start at 0, because I'm already adding a to it. And then my final piece would be probably a plus l. In this case, if I choose x, I would just set my limits to be a to a plus l. So it doesn't matter. You can do what you suggested, and it'll be just fine. Okay? The reason I'm not is because I'm picking, I wanted to, it's simpler. That piece is a distance x away from a, and it will be my working variable during integration. But you can do it your way. It'll work just the same. Yep.
Is the piece you chose for dx, is that like directly at the center of the bar? Or is it just that?
No, it's just some place on the bar. I don't know where it is. Am I good to keep going? Usually, at this point, I would start asking myself, is there any directional symmetry? Meaning, is the direction of the force going to have components in more than one dimension where one might cancel out? But I don't have to worry about this here, because I think we all agreed at the very beginning that every piece of the bar pushes in the same direction. So I don't have to worry about anything like that. I can construct my force equation now. How much force does this one piece cause? Now, I'll wait a second for you guys to give that a shot. Now, I hope you all started with Coulomb's law. I'm starting with a super simple framework for Coulomb's law. I haven't subbed anything in except for dq. Now I'm going to start subbing in pieces. think that's it. Yes?
I was just wondering why we didn't have the A portion. Is that just because it's one dimensional?
I don't have the A there because I decided to make my measurement start from Q.
I
Yeah.
thought x squared was not allowed to be multiplied by x squared.
Can't be. But x squared does tell me where that piece is. I'm going to have to find a way to get rid of it. You're right. But you'll notice I got right up to the end and left x in it the last time. But I was going to have to integrate. And at the end, I was going to substitute something in. All right, so my next job here is to kind of pull all of the things that are constant to one side and to perhaps organize this and define some limits. So I'd like us all to do that. Can you look for things that don't have anything to do with x, pull them to the left, and you can take the things that have to do with x and push them to the right. How about that? Any question about what I did? Yep. Well, I took everything that was here and pulled it away and pushed the x over there. I had to have something that stayed in the numerator. I'm okay so far? All right, so that represents one piece of the total force because it's only one piece of the total bar. If I want the entire force, I need to add up all of the pieces, which means adding up the whole bar. Now I'm adding the summation symbol. I am placing the summation symbol in the middle because everything on the left has nothing to do with x. None of this has to do with where I am on the bar. But this stuff does. And I'm going to tell it where to start. I'm going to start a distance a away from my point charge. And I'm going to tell it where to end. That should do it. Now, not everybody, but the vast majority of you in the room should be able to do this antiderivative. Because many of you have calculus or in mechanics last year, and this one's a piece of cake. Now, I'm not saying that all of you do or even remember. I'm not asking about that. I will teach you this. But again, that's the least interesting part of the problem. If you can do this summation, though, you can get the answer. I want to do it because there's enough people who can. If you can't, don't feel like I'm expecting you to know how to do this next part. But I want the people who can do this to exercise that part of their brain. So you guys who can, make it happen. You guys who can't, pay attention. For the time being, we're going to write this a little different. The polynomial rule works here. So we're going to use the polynomial rule. And for those of you who have had calculus, you know what the polynomial rule is. When finding the antiderivative, you add 1 to the integral. You add 1 to the exponent, and then divide by the new exponent. So everybody who's had calculus or is in mechanics knows that. You guys who don't know that, we're going to go over all of it. I'm going to teach you how to do it. I'm just trying to utilize some prior knowledge from some people. that means we first open parenthesis here and write in our antiderivative, which is x to the -1 divided by -1. We get rid of the dx now because we found the antiderivative. And we put a bracket here to remind us to plug in our limits. Again, from here down, I'm only asking people who are familiar to do this. You shouldn't get yourself concerned. We'll do this a lot of times. You'll be good. From there down. However, at this point, this is just algebra. The calculus was just finding the antiderivative. So this will be -1 over a plus L minus -1 over a. We're plugging in our limits. You put in your upper limit, and you subtract your lower limit. That's the answer. You should clean it up. That's the answer. Best way to clean it up is to get common denominators. And of course, flip it so that it's a positive. It's going to be a positive answer. Yes, sir?
So I just have a question about the limit. I understand where you got a plus L from, but I'm still kind of confused where you got A.
Where I got A?
Yeah, with the and the bottom. I thought it would be from like dx.
The particle is here. So where's the first piece of the bar? The first piece of the bar has to be here. How far away is that from where I am?
A?
Yeah.
I thought
So-
you were putting it to the dx.
No. dx is just somewhere in the middle.
Oh, okay.
Will I get to dx? Will I get to where this piece is? Yeah, sometime. But my x represents a way of pointing to every piece of the bar. I just have to tell the integral where's the first piece and where's the last piece. That's all I have to tell it. It will fill in the middle. Is that okay?
Yeah.
All right, since we are right there, and because I like a little bit of closure, and because there's something here you need to see. This is 1 over a minus 1 over a plus L. And you should get common denominators, which in this case would be a times a plus L. The numerator would be a plus L minus a. You all following okay? I'm just doing algebra. This is stuff you all know. Well, kind of know. But there's a good reason to do this. You see that a plus L minus a gets rid of the a, don't you? So I get kind of an interesting result. Q, K over L times L over a times a plus L. Yeah, you see it, right? I know. I see it too. And if I keep going just a little bit here, and I know it's going to freak some of you out a little bit, but this is the whole force. It's kind of funny if you look at it, though, isn't it? The denominator is a distance squared. Has to be, because Coulomb's law is a distance squared. The bottom is the product of the first part of the bar and the last part of the bar. Weird. Interesting. Weird. Yeah, I like it. Kind of fits my sensibilities. L gets bigger, the total amount of force gets smaller because the charges get further away. Makes sense. If A gets smaller, force gets bigger because the whole bar is getting closer to my point charge. All of that makes sense to me. So it has some sensibilities about it that makes sense. Yes, sir.
So I have another question about the limits for the integral of the subtract. Why wouldn't, like, if it's the integral, the sum of all the charges acting on the point Q, why doesn't it start at the start of the bar rather than the end of the bar? Like, instead of doing, like, shouldn't it go from 0 to a plus L?
Only if the bar is a distance 0 away from the charge. That would mean the bar started right here. Right where the charge is.
But isn't the very left side of the bar just 0?
Here?
Yeah.
What distance is that away from my charge?
A plus O.
That's a plus L away. That's the farthest piece away.
Oh, you had it flipped. Something like what I thought.
The bottom limit is where the first charge appears. The top limit is where the last charge appears. Now you could have flipped those limits and your answer will come out to be the same. You're just adding it in the a different order. Because you're adding it from outside to inside, you'll have to put a negative sign out front. I don't want to go into that part either. I've trained you to do from the closest piece to the furthest piece on purpose. But I'm not sure where the question's coming from, except that I think some people wanted to put x plus a as our starting point in there somehow. But we do that when we're setting it up. But I'll answer whatever other questions I can here related to the setup. Yes, sir?
For the final answer, when you increase, as you increase L, the answer gets smaller.
Yeah.
Does it make sense? Because aren't you getting more charges?
No. The total charge isn't changing. You're just taking a bar and spreading it out more. Wouldn't that mean that if the charge stayed the same, but some of the pieces are now further away, wouldn't they affect Q different? And I would think it would go down. We're not adding more charge, right? We're just taking the bar and making it longer. So in effect, we're diluting the charge. Yeah.
On the second line with the integral df equals, what would be the limits of df? I know it doesn't matter when you
0 to f.
Okay.
0 being the charge, the force you get without any charges, get applied. F being the total force. So, I mean, technically I could put this here and that'd be okay. I'm adding up the total force, but the sum of a differential like this is the total.
Because you have x, and then when you do you just have f minus 0, right? Whenever you solve for the integral, you just have your new expression be x with the limits from 0 to f.
Yeah.
Okay.
Right, because, I mean, truthfully, there's a 1 here, which is f to the 0 power. Yeah. Okay, so I like using the bar. The bar provides us with an answer that most of you can successfully do. Some of you can't, but your success is only hampered by this. The only thing that calculus actually trains you on, which is finding an antiderivative. You'll spend the entire second semester and part of the first semester looking at different antiderivatives and ways of getting them as they become more complicated. You guys have had calculus, am I wrong? I mean, you learn other things too, important things, about how to fend for yourself in this world, but basically it comes down to, here's an expression, can you find an antiderivative that'll work for this integral? And if you can't, here are some tools. And you learn different tools. What I need you to understand is that the only tool I'll require in this class is U sub. And for the most part, all integrals are on the integral table that'll be provided in the book, or provided on the equation sheet. I do not need you to be an expert here. I'll remind you, this is 1 point. Believe it or not, if this were on the exam, this is likely to be 1 point. This is what they consider to be the calculus. And it's mathematical. This is likely to be worth 3 points. So if you can get to here, you can get a 5 on the exam. You can lose a point. It's about this. It's about choosing this correctly. The bell rings in a minute. Please understand that the very next one we're going to do
Oh my God.
which will also be the last one we're going to do, is a semicircular bar of charge. There's no joke. I'm not sure why they're laughing. This one's actually super, super simple. if you wait, before you guys leave, and let me finish, please, guys. I didn't work this hard just not to finish. It's a semicircular bar of charge. If we're at the center of that circle, every piece of charge is the same distance away. So Q dq k over whatever the radius is squared, this is now a constant. It's not part of our integration. So sometimes it might look more complicated than it is. I told you, we only get 3 shapes: straight lines, curves, and circles. There's a reason for that. All right, bye. Well, with this question, I said we'd bring a charged particle towards the middle of the number line. And our goal is trying to figure out what would be the force on this charged particle. Now, I think there's an obviousness to this problem, that you could start by pairing this charge up with every single charge that's there. And we discussed the idea that there's some symmetry that can be exploited first. That if we know, say, this distance, A, and we say that every charge is spaced a distance d apart, well, we could probably come up with an expression that we could use over and over and over again to try and figure out what the total force on the yellow charge would be. Do you guys remember doing this?
Yes.
It's a summation. And if you're comfortable with the summation terminology, you probably could create a summation expression that would, if summed correctly, give you the total amount of force on the particle. I don't want to spend a lot of time with that, but I do want the idea of a sum to be a thing here. That you can create a single expression where you could increment a number, and by incrementing that number, you could work through a sum. So if you remember what we did for this problem, we picked one of the charges, say that one, and came up with what its expression would be for the force on the particle. And it was relatively straightforward. We connected the 2 particles together. We recognized that that distance would be r. And even though r couldn't likely be in our answer, so I'll write it blue, we knew we could write r in terms of other things, a squared plus d squared. We recognize that there is a certain amount of symmetry, and because of that symmetry, we could scale the force and look at only one of the 2 possible components, meaning we could see that there is a component of the force in this direction, and that one matters, but that there's a component of the force in this direction, but this one, this one matters less because we know that there's a particle over here that'll provide an equal and opposite horizontal component. So that allowed us to identify an angle theta here and recognize that the force we want isn't F, but F cosine theta. All of this should look familiar to you. That's something we've already kind of done. Now, from here, we could construct a force equation. And that would look probably something like this. If each of these is capital Q, just so I have a way of differentiating, and this one lowercase q, then I think I could write an expression, force equals Q, Q, K over R squared. And then slowly work in the variables we're allowed to have. Like the first thing I would probably do is say, okay, I want to scale it in the direction that we need. And I might be multiplying by a certain number of these, or I might be doing something to help me understand how many of these contributions there are. Knowing that we can't have theta in our answer and knowing that we can't have r in our answer, we would have worked to try and find ways to write r in terms of the given variables, a and d. We'd get something like that. And knowing that we can't have theta in our answer, we'd have to work to apply some meaningful geometry to get rid of theta. And I hope that you guys all saw that in this one, it would be a over the square root of a squared plus d squared. That would be the corresponding way of doing cosine. We've done all of these before. All this is stuff we've already done. I don't know that you would be super successful, but I'm hoping you'd be a little successful. And then I could combine it all. Q, K times A all over a squared plus d squared to the 3/2 power. Now that is these two. Everything good so far? Well, there's clearly a lot of these. But do they change very much when I go from one to the next? I mean, I could start with the center. The center, I wouldn't have this d at all. So if I was to start with the center charge, I might be able to say, okay, the center charge is Q, K, A over a squared plus 0 times d squared to the 3/2. I could go to the one right next to it and know that that one's going to be Q, K, A over a squared plus 1 times d squared to the 3/2 power. And I would probably also have to, even though I haven't done this yet, I'd probably also have to realize that it's 1d quantity squared, because I'm going to go to the next charge, which is 2d away, and that whole quantity is probably going to need to be squared for it to work out. And that's what I would do. So now I look at this particle, and there would be QK over a squared plus 2d squared to the 3/2 power. And you know I'm going to keep going, right? Each time incrementing this number a little bit. And then I would probably have to make some other reasoned arguments, like there's two of these, one on each side of 0. And there's two of these, one on each side of 0. And so on and so forth. These all things you guys can follow so far? I haven't done anything really crazy yet, right? Now we have a way to do this. Right? We have a method. There's a way to write this. Now whether you guys have learned this or not, you should have, because my understanding is it's a pre-calc thing. But I was talking with Mr. Gilbert, and he's told me that several things that I expected to be in pre-calc have been removed in the last couple of years. So I don't know if you learned this or not. More importantly, I don't know whether if it was presented, you actually learned it. But I could talk about the net force being a summation of all of this. Now, I probably wouldn't include this in my summation because that one's not doubled. But I can include all of these in the summation because they are doubled and they're all exactly the same. So I might be resigned to write QQKA over a squared plus 0d squared to the 3/2, just to write it out there. But then I might say plus the summation. Now, do you guys know how summations are supposed to be written? That's too bad. There's a rule or set of rules for how summations are supposed to be written. First, we have to identify an incrementing variable, something that would allow us to increment the number of things we're going to add together. I'm probably going to go with n. Sometimes they use I. I don't really care. N is just nice because it's a number, a counter. And I'm going to start at n equals 1 because that's the first one that has to be doubled. And in there, I'm going to have, okay, my expression 2 q q k a all over a squared plus n d squared to the 3/2. Now on the top, I'm supposed to tell it how many of these to count. And I could pick whatever I want here, depending on what the problem is. If the problem tells me that there's a total of 9 of these, well, the first one's at the center, so I would do this from n equals 1 to 4, and I would do the 4 that are on either side. There's an infinite number of them, well, then, by gosh, just put infinity there, and just keep adding all the way to the last one, which is infinitely in both directions. This is a summation. Now, I look at this summation and realize that as n goes to infinity, this term goes to 0. There might be a way to do this recursive sum. But this is how a summation works. It adds up each contribution to the total. Now, you may not understand why I spent so much time talking about this example, except the thing that we're doing here. Except here, we have this kind of finite way of expressing one of the forces, right? We have this clear incrementing number here. And this incrementing number is actually incrementing a distance. It's telling us what the distance is between here and here. So if it's 2 particles away, it's 2 times the separation distance, 2d. But that's the value that's incrementing, right? How far away the charge is from the center. We want to do something similar, but we're not going to have anything that is so tangible, like a fixed particle. So we were doing here, right? We created a summation, an instruction set that told us if I wanted the entire force, I would use a summation, which could give me a method of finding out the entire force. What happened over here? Every part of the term that didn't change when we went from n1 to n2, we could take out of that summation. It wasn't part of the summation. Every term is being multiplied by that same value. On the other hand, the denominator here, every time I add 1 to n, that entire denominator changes. There's nothing I can factor out of that, nothing I can get rid of and pull out front. If n goes from n1 to n2, everything about that denominator is now a different number. This one's based on discrete individual pieces.